Hi chemists, my name is Kim, and today we are going to be talking a little bit more about electrolytic cells in the context of using hydrogen in a fuel cell to be able to generate carbon-free electricity in the future. Super cool, right? So our learning goals are to explain how a hydrogen fuel cell could work to produce electricity without emitting greenhouse gases, the way that our other forms of electricity production, such as burning fossil fuels, do. We also are going to explain why an electrolytic cell is needed to generate hydrogen gas that can then be used in the hydrogen fuel cell. And we will practice identifying where reduction and oxidation are actually occurring in an electrolytic cell. Let's go. So just a quick reminder that an electrochemical cell is any type of cell that can convert electrical energy to chemical energy or vice versa. If we are attempting to use chemicals to get electrical energy or electricity, we would want to use a voltaic cell. So a hydrogen fuel cell is actually a form of a voltaic cell. We would need to use an electrolytic cell if we were trying to generate a chemical, and making that chemical required a reaction that was not spontaneous. So you can think about voltaic cells and electrolytic cells as the opposite of each other. A voltaic cell is a chemical reaction that occurs spontaneously and releases energy, or allows energy to be released during a redox reaction, while an electrolytic cell is non-spontaneous, and we need to use electricity or some form of energy input. Doesn't always have to be electricity, but that's what it traditionally has been, to generate a chemical through a redox reaction. If we take a look at table I, and this is a little bit of an oversimplification of some more complex engineering and physical chemistry ideas, but it will suffice for our purposes today. If we look at table I and we notice the note at the bottom that says the delta H values are based on molar quantities, a minus sign indicates an exothermic reaction. Remember, an exothermic reaction releases energy to the surroundings. Traditionally, humans have harnessed exothermic reactions to generate electricity in power plants, particularly power plants that use steam, heated up water, to turn a turbine. The most common thermal power plants, or power plants that use boiled water to turn a turbine, are those that burn fossil fuels. So oil, natural gas, and coal are made of carbon, and they undergo exothermic combustion reaction. Now, the top 6 reactions in table I are all combustion reactions, and notice how much energy they are all releasing, particularly those top 6. They're releasing a lot of energy. This is why humans have used fossil fuels for so long to generate electricity. They are very exothermic reactions, the combustion of these hydrocarbons. However, see that product there in all of the reactions here? You know what that product is called? That's carbon dioxide. And the problem with using carbon dioxide as a product in these reactions is that it is a greenhouse gas. So when we are emitting carbon dioxide into the air by burning fossil fuels like oil, natural gas, and coal, which all undergo a very similar combustion reaction, and the product would be CO2 plus H2O, we are contributing to climate change. And so one of the major goals to have a more sustainable future is to find a way to use an exothermic reaction to generate electricity that does not release carbon dioxide. Now, this is where, as fossil fuels are becoming more expensive and less available, and we know that they are bad for the environment to burn, scientists are looking for other energy sources. It turns out hydrogen, just simple, smallest element on the periodic table, hydrogen, has long been considered a really good source, because when you combine hydrogen with oxygen in a reaction where it burns, it does not pollute, it does not create carbon dioxide. Let's take a look back at table I, and let's see if we can find hydrogen reacting with oxygen on there. So take a moment to scan table I, look for a place where hydrogen is reacting with oxygen to form water. I see some H2 plus O2 gas. The difference between these two reactions is that one of them is forming liquid water and the other is forming gaseous water, but they both, notice, are very exothermic. So it turns out synthesizing, remember, a synthesis reaction takes 2 different substances and puts them together into one compound. So this synthesis reaction releases energy. This is really exciting because this reaction could be used in a voltaic cell. Let's take a look at this fuel cell that has the reaction occurring and think about what's really going on here. So this is showing us our reaction, our H2 reacting with O2 to form H2O. And to prove to us that this is generating electrical energy, we see electrons moving through the wire. That is electrical energy, right? The fact those electrons are moving through that wire there, they're lighting up the light. This is energy being released from this synthesis reaction. Let's relate this to redox. It's so exciting how this part of the unit can relate to so many things that we've talked about this year. So on this side of the electrochemical cell, I have hydrogen gas that is becoming, let me make this a little bigger here, H2 gas becoming an H plus ion. So H2 gas, let's think about oxidation states, right? H2, hydrogen by itself, H2, that will have an oxidation state of 0, right? Because any element by itself has an oxidation state of 0. And a hydrogen ion with a charge of +1, well, that's pretty straightforward. That would have an oxidation state of +1. So what's happening over here? What's happening to hydrogen? Is hydrogen being oxidized or is it being reduced over here? Think about that for a moment. So hydrogen is being oxidized in this particular cell, right? This is a voltaic cell because it is converting chemical into electrical energy. It also is an example of how a hydrogen fuel cell works. Now over here on the other side of the fuel cell, we have oxygen gas. We're starting off with oxygen gas. You see the O2 entering, which, oxygen gas just floats around. Here it is. Oxygen gas just floats around in our atmosphere. So we're starting off with oxygen gas, which has an oxidation state of 0. And we notice these electrons are moving towards the oxygen there. And the oxygen is ending up in a compound with H2O. That tells me that oxygen, when it ends up as H2O, it must have an oxidation state of -2. I can tell this from looking back at the periodic table. If I do that, I'll see that the only oxidation state for oxygen is -2 when it's in a compound. But I also can just kind of use reasoning here. It's a neutral compound and it's bonding with 2 + 1 oxidation state hydrogens. So it must have an oxidation state of -2. So that tells me that over here, oxygen is being reduced. So if I want to think about which side is my anode and which side is my cathode, I'd like you to think for a moment and think, where is my anode and where is my cathode? My anode would be over here with hydrogen and my cathode would be over here with oxygen, because we can remember the abbreviation REDCat, and ox. So hydrogen would be going in at the anode, oxygen would be going in at the cathode. And this reaction right here would be releasing many kilojoules of energy. And in some situations, that energy can be used like a battery, right, to generate electricity. So this is the idea. If we just have lots and lots and lots of hydrogen gas as a starting material, we already have lots of oxygen gas in the atmosphere, so we don't have to worry about getting that. But if we could just have hydrogen gas, which is not quite as available to us as oxygen gas, if we could just get hydrogen gas, we could do this reaction that would allow us to release energy without releasing carbon dioxide. Sounds pretty great, doesn't it? This is where we're going to end part 1 of this video. To continue watching to finish achieving all the learning goals that were listed at the beginning, make sure you go find part 2 of this video, which will be right up next in the queue.